Good morning, good afternoon, and good evening to everyone who joins us from around the world. This is Stack Series, and we're so glad you're here. This is Andrea and Renee. Welcome to the podcast.
Today we are exploring topological data analysis, deep learning, and the physics of topological matter.
Now, I know what you're thinking.
Yeah.
That is a mouthful of a title. It sounds like something you'd see written on a chalkboard in a movie about a genius mathematician who is about to solve the secrets of the universe.
And in a way, that is exactly what it is.
Right. But the reason we picked this stack of sources today, from Archivist papers to Princeton Research News, is because it feels like we've been handed a map to a hidden dimension. We usually go through life thinking the world is made of rigid things, hard numbers, solid objects, straight lines.
But the research suggests that if you look close enough, whether at a spreadsheet of data or an electron moving through a wire, the world is actually much more fluid. It's stretchy. It's all about shape.
So here's the plan. We're going to break this down into three big chunks. We're going to look at data, then artificial intelligence, and finally quantum physics. And the glue holding this all together is this concept of topology.
It is a pleasure to be here. And frankly, the topics we are covering today represent one of the most significant shifts in how we understand reality, both in the digital world of artificial intelligence and the physical world of quantum matter. It's a convergence of fields that usually stay in their own lanes.
Absolutely. And I want to start with a mental image that I think most of our listeners will recognize. It's the default setting for how we think about information or data. When I say data, you probably picture a spreadsheet, right?
Equal sheets.
Exactly. Infinite rows, infinite columns, just a wall of numbers. It feels rigid. It feels like a grid. You have row 4, column B. It's very precise.
Precisely. That is the classical view. You have points, you have coordinates, and you have values. It's a very Cartesian way of looking at the world. X, Y, and Z, everything in its box.
But the premise of the research we have in front of us today challenges that completely. The central question we're looking at is, what if data has a shape? What if, instead of just a grid, that cloud of data points actually looks like a donut, or a void, or a complex knot? And more importantly, what if that shape tells us more than the numbers themselves?
That is the core question. And our mission today is to explore how the field of topology, which is essentially the mathematical study of shape and connectivity, is revolutionizing three distinct yet deeply interconnected fields. First, we have data science, where we are trying to understand massive, messy data sets that break our traditional spreadsheets.
Then we have artificial intelligence.
Specifically, how we make neural networks smarter and more robust. And third, and perhaps most mind-bendingly, quantum physics, where this concept of shape is actually allowing us to create entirely new states of matter.
It's a huge scope. We're going from looking at spreadsheets to looking at the fabric of the universe.
Yeah. In a way, yes. Because the mathematics describing both are surprisingly similar. Whether you are looking at the shape of a social network or the shape of an electron's wave function, the rules of connectivity, the topology, apply to both.
And just to tease what's coming, later in our exploration, we're going to be talking about something called the Manifold Hypothesis, which basically suggests that reality is a lot simpler than it looks if you just know how to unfold it. And even later, we're going to get to a particle that sounds like it's straight out of science fiction, the Majorana fermion.
Ah, yes, the magic particle.
The magic particle that is its own antiparticle and might just be the thing that saves quantum computing from being a noisy mess.
It is a fascinating journey. It connects the very abstract world of pure math with the very concrete engineering challenges of the next century.
Okay, let's unpack this. We have to start with the basics. We keep saying topology. For the uninitiated, or for those of us who haven't opened a math textbook in 20 years, what exactly is topology? Because when I hear geometry, I think of triangles, protractors, and trying to calculate the area of a circle.
That's the right place to start. The best way to think about topology is as geometry without measurement.
Geometry without measurement. That sounds like building a house without a tape measure. How does that work?
Well, in traditional geometry, Euclidean geometry, you care deeply about angles. You care about precise distances. Is this line straight? Is this angle exactly 90 degrees? If you bend a triangle, it stops being a triangle, right?
Right. It becomes a bent line or a curve.
But topology doesn't care about any of that rigidness. It cares about connectivity. It cares about how things are attached to each other. And crucially, it cares about holes. It asks, is this object one solid piece? Does it have a hole through it? Is it knotted?
This brings us to the classic analogy that I saw in the source material, the coffee mug and the donut. I feel like this is the hello world of topology. If you take a topology class, This is day one.
It is the classic for a reason. To a topologist, a coffee mug and a donut are the exact same object. They are indistinguishable.
Okay, hold on. If I try to pour coffee into a donut, I'm going to have a mess on my table. So clearly, they're different in function.
But mathematically,
Mathematically, they are the same because they both have exactly one hole. The donut has the hole in the center. The coffee mug has the hole in the handle.
okay, I'm with you.
Now, here is the mental exercise. Imagine them made of a very soft, flexible rubber sheet, clay or Play-Doh. You could take the coffee mug, squish the cup part flat, so it's just a lump of clay, and then widen the handle loop until it looks exactly like a donut.
And the key rule here is I can't rip it. Exactly. You cannot tear the material, and you cannot glue any new parts together. You can only stretch, bend, twist, and compress. Because you can deform the mug into the donut continuously without breaking it. They are topologically equivalent. We call this homeomorphism.
Okay, so a mug is a donut. What isn't a donut? What about, say, a pretzel?
Oh, a pretzel is a great example. A classic soft pretzel has, what, 3 holes?
3 holes, yeah.
So to a topologist, a pretzel is not a donut. To turn a donut into a pretzel, you'd have to punch 2 new holes in it. You're changing its fundamental connectivity.
What about something like a bowl? It has an opening, but it doesn't go all the way through.
A bowl is actually the same as a sphere or a basketball. You can take a flat sheet of clay and press your thumb in the middle to make a bowl shape. You can also smooth that back out into a flat disc and then puff it up into a sphere. No new holes were created. So topologically, a bowl, a plate, and a basketball are all the same thing. They're all genus 0, meaning 0 holes.
It's like looking for the soul of the shape rather than the specific dimension.
That is a poetic way to put it, but yes. It ignores the superficial detail. Is it big? Is it small? Is it bumpy? And looks at the fundamental structure. Does it have a hole?
Okay, that makes sense for rubber sheets and donuts. It's fun to think about.
Yeah.
But we are talking about data. We are talking about gene sequences, financial transactions, pixels in an image. Why does rubber sheet geometry matter when I'm analyzing a spreadsheet of sales figures?
It matters because traditional statistical analysis has a major blind spot. Think about how we usually analyze data. We look for linear relationships, straight lines. We want to draw a regression line through a scatter plot. Or we look for simple clusters, blobs of data here, blobs of data there.
Right. We want a line of best fit. We want to say as X goes up, Y goes up. That's the dream.
But the real world is rarely linear. As we saw in the research, real-world data, whether it's genomic data or image recognition data, is high-dimensional, it is noisy, and it is messy. It doesn't sit on a straight line. It loops, it branches, it has voids.
So if I use a linear tool on a loops dataset, I'm missing the point. I'm trying to fit a square peg in a round hole, literally.
You are missing the global structure. You might see a few points close together and think they are related, but you miss the fact that they are part of a giant circle. Traditional metrics often fail to see the forest for the trees. They get lost in the local noise, the jitter of individual data points, and miss the overarching shape of the data.
So topology allows us to step back and say, hey, ignore the noisy jitter of the individual points. What is the overall shape here?
Precisely. It extracts features that are robust. It finds the signal that persists even when the data is stretched or squished by noise. It allows us to ask qualitative questions about data, not just quantitative ones.
That leads us perfectly into the toolkit. The sources talk a lot about topological data analysis, or TDA, and the heavy hitter here seems to be something called persistent homology. Now, I had to admit, when I first read persistent homology, my eyes glazed over a bit. It sounds intimidating.
It sounds technical, I'll grant you that, but the intuition behind it is actually quite beautiful and surprisingly visual. Imagine you have a data set. Let's say it's a point cloud.
A point cloud, okay.
Just thousands of little dots floating in 3D space. Maybe these dots represent stars in a galaxy or customers in a market.
Okay, I'm picturing a swarm of bees or stars. Just points suspended in the air.
Right. Now, if you zoom in really close, all you see are isolated dots. There is no shape. Just dots. But let's play a game. Imagine expanding a little bubble around each dot.
Okay, like a soap bubble growing around every single data point simultaneously.
Exactly. This process is called filtration. You slowly increase the radius of these bubbles. At first, the bubbles are separate, but as they grow, they start to touch and merge.
And when they merge, they form shapes. 2 bubbles merging become a blob.
Yes. And this is where the topology comes in. We look at what structures form as these bubbles merge. At the lowest level, dimension 0, we just have connected blobs. Clusters. This is what standard clustering algorithms find.
Okay, that's easy enough. That's the local stuff. Neighbors connecting to neighbors.
But as the bubbles keep growing, something interesting happens. Imagine your data points are arranged in a big circle. As the bubbles along the circle merge, they eventually form a continuous chain that loops back on itself. That creates a hole in the middle.
Oh, I see. Like a pearl necklace where the pearls swell up until they touch, forming a solid ring.
Exactly. That is a dimension 1 feature, a loop.
And if I have a hollow sphere of data points, like a soccer ball, eventually those bubbles merge to form a shell with empty space inside.
Yes, that is a dimension 2 feature of void, a bubble with empty space completely trapped inside.
So we are watching this movie of bubbles growing, this filtration process, and we are tracking when these holes and voids appear.
And crucially, when they disappear, because eventually if the bubbles get huge, like giant beach balls, they will swallow up the hole. The hole is filled in.
And this brings us to the persistent part of persistent homology.
Right. We track the birth of a feature when a hole appears and the death of a feature when it gets filled in. The difference between the birth and death is its persistence.
And I assume the idea is that if a hole appears and then immediately disappears, it was probably just a fluke.
Exactly. If a feature has a very short lifespan in our filtration movie, it's likely just noise, a little gap between 2 points that didn't mean anything. But if a feature persists, if a loop appears and stays open for a long range of bubble sizes, that tells us something fundamental about the structure of the data. That is a real signal.
I love that. It's a way of distinguishing signal from noise without having to guess what the right scale is. Usually in data analysis, you have to decide, am I looking at the micro level or the macro level? TDA seems to say, look at all levels at once.
That is the power of it. It is multi-scale. You don't need to know beforehand if you are looking for small loops or big loops. The analysis shows you all of them. It removes human bias from the scale selection.
The sources mention some specific visualization tools for this. Because obviously we can't just look at a spreadsheet of birth and death times. They talk about the barcode and the persistence diagram.
Yes. The barcode is very intuitive. Imagine a graph where the horizontal axis is the size of the bubbles. For every topological feature, every loop or void, we draw a horizontal bar. The bar starts when the feature is born and ends when it dies.
So if I'm looking at this graph, I'm essentially scanning for the long lines.
You are looking for the long bars. A long bar means a persistent feature, a truly significant structure in your data. The short little bars that look like stubble at the bottom, that's the noise, that's the jitter.
And the persistence diagram.
That's a scatter plot. You plot birth time on the x-axis and death time on the y-axis. Points that are far away from the diagonal line, meaning they died much later than they were born, are your significant features. Points hugging the diagonal are the noise.
It's amazing that we can take something as abstract as the shape of a data set and turn it into a rigorous chart that separates truth from mess. It feels like we're distilling the essence of the data.
It gives us a new pair of glasses to look at data. Instead of just statistics, we see structure. And once you see the structure, you can start to understand the why behind the data.
So we've got this toolkit. We can see shapes in high dimensions. And I want to connect this to artificial intelligence because the sources mention the Manifold Hypothesis. And this seems to be the bridge between maths and deep learning.
It is fundamental. We often talk about big data having hundreds or thousands of variables. An image, for instance. A small 1,000 pixel image is technically a point in a 1,000 dimensional space.
Which is impossible for the human brain to visualize. We tap out at 3D, maybe 4D if we had time. But 1,000 dimensions, I can't even picture what a direction looks like in 1,000 dimensions.
Impossible. But the manifold hypothesis suggests that even though the data is technically in 1,000 dimensions, the meaningful data points don't occupy that whole space. They are actually huddled together on a much lower dimensional surface, a manifold that is curved and twisted inside that high dimensional space.
The analogy I've seen is a crumpled ball of paper.
Yes.
The paper itself is a 2D surface. It's flat. I can write on it. It has height and width. But if I crumple it up into a tight ball, it exists in 3D space. It looks complex and chaotic.
That is a perfect analogy. The crumpled ball is your raw, high-dimensional data. It looks complex and 3D, but the underlying reality of the information written on the paper is actually just 2D. It's simpler. The complexity is an illusion caused by the crumpling.
And the goal of machine learning is to smooth out the paper.
Essentially, yes. We want to unroll or flatten that manifold so we can read what is written on it. When a neural network classifies images, it is trying to twist and stretch the data space until the cat manifold is separated from the dog manifold. It's uncrumpling the paper to separate the messages.
But neural networks are often criticized for being black boxes. We feed data in, Magic happens, and an answer comes out. We don't always know how it learned to unroll the paper. Sometimes it unrolls it in weird ways.
And this is where topological deep learning, or TDL, comes in. Researchers are now actually embedding topological tools directly into the neural networks. We aren't just using TDA to analyze the data before it goes in, we are using it during the learning process.
How does that help?
Well, think about regularization. We can tell the network, learn to classify this data, but minimize the topological complexity. We can penalize the network if it creates a representation that is too fractured or has too many unnecessary holes. It guides the AI to find a smoother, simpler solution.
So it's like giving the AI a rule. Keep it simple. Don't tear the paper if you don't have to.
Exactly. It forces the model to respect the underlying topology of the data. And another massive application is pruning. Modern neural networks are huge, billions of parameters. They're expensive to run and slow.
Right, they take massive server farms to train. The carbon footprint of training a large language model is actually significant.
But do we need all those connections? TDA can analyze the flow of data through the network. We can use persistent homology to see which weights, which connections are actually contributing to the topological structure of the data flow.
And if a connection isn't contributing to that structure,
We cut it, we prune it, we treat the neural network itself as a data set and look for the topological signal.
it's like a gardener trimming a hedge. Or better yet, like the human brain. When we are kids, we have way too many connections, right? And as we learn, we prune the ones we don't need.
That is a very apt comparison. We are making the artificial brain more efficient by removing the noise. And the results are impressive. You can make models significantly smaller and faster without losing accuracy because you are preserving the essential shape of the information flow while discarding the redundant noise.
There's one more AI application in the notes that I found really distinct. Adversarial robustness. This is the security angle.
This is a critical issue. You've probably heard of adversarial attacks. You take a picture of a panda and you change a few pixels, changes so subtle the human eye can't see them, but you feed it to an AI and suddenly the AI says, that is a gibbon or that is a school bus.
It completely breaks the model. And it's terrifying if you think about self-driving cars. If someone puts a sticker on a stop sign that makes the car think it's a speed limit sign,
Exactly. It's dangerous. But here is why it happens. Standard AI looks at pixel values. The attack changes the pixel values, which moves the data point just enough to cross a decision boundary in the AI.
so how does topology fix this?
Well, usually these attacks disrupt the local topological structure. The pixels change, but the distribution of the data around that image looks topologically wrong compared to a real image. A real image of a panda sits on the panda manifold. The adversarial image might have crossed the line, but it doesn't sit comfortably on the gibbon manifold. It's floating in no man's land.
It's like a lie detector. The image might look like a panda to the pixels, but the shape of the data feels artificial.
Precisely. TDA can detect these attacks by noticing that the data distribution has been tampered with. It sees that the manifold has been distorted in a way that natural data wouldn't be. It provides a structural defense mechanism that goes deeper than just the surface appearance.
That is incredibly reassuring. It's moving AI from just pattern matching to actually understanding structural integrity. It feels like giving the AI common sense, in a way.
It is a step toward making AI more reliable, interpretable, and safe.
Let's shift gears. We've talked about data and AI. I want to move to the wet, messy world of biology. Because if there's anything that is high-dimensional and chaotic, it's life.
Biology is the ultimate playground for topology. There is no grid in biology. Everything squishes, everything moves. Think about proteins.
Proteins are the workhorses of the cell. They do everything. They digest our food, they move our muscles.
And chemically, they're just long chains of amino acids. But a chain in a straight line doesn't do anything. To function, that chain has to fold up into a very specific, complex 3D structure. The function of the protein is determined by its shape. If it folds wrong, it doesn't work, or worse, it creates toxic clumps, which is what happens in diseases like Alzheimer's.
And I imagine describing that shape is hard. It's not just a sphere or a cube, it's a tangle. It looks like a ball of yarn after a cat played with it.
It is a knot, and this is where knot theory, a branch of topology, comes in. The sources mention the Gauss linking integral and Jones polynomials. These are mathematical tools designed to quantify exactly how tangled a cloud is.
So we can calculate a number that tells us exactly how knotted a protein is.
Yes, and this is vital for drug discovery. The classic analogy for drugs is a lock and key. The protein is the lock, and the drug molecule is the key. You want the key to fit the lock to either turn it on or block it.
But I'm guessing It's not as simple as fitting a geometric shape into a hole, like a key in a door.
No, because these molecules are flexible. They breathe, they vibrate. A geometric fit isn't enough. You need a topological fit. You need to understand the pocket in the protein, not just as a rigid shape, but as a topological space that the drug needs to interact with.
So TDA helps us predict ligand binding, how well the drug sticks, by analyzing the topology of the protein pocket.
Exactly. It allows us to screen millions of potential drug molecules and say, this one has the right topological signature to fit into this protein's complex knot structure.
That could save years in the lab. Usually, pharma is just trial and error, right?
Yeah.
Spaghetti at the wall to see what sticks.
It absolutely does. It moves drug discovery from alchemy to engineering and extends to genomics, too.
Right.
The research discusses single-cell genomics.
This is where we analyze thousands of individual cells to see what they're doing, right?
Yes. In the past, we would just take a chunk of tissue, say a piece of liver grinded up, and sequence the average. But that averages out everything. You lose the nuance.
It's like analyzing the average income of a city. If you just look at the average, you miss the billionaires and you miss the people in poverty. You assume everyone is middle class.
Exactly. In biology, the interesting stuff is often in the outliers. The rare stem cell that can regenerate tissue. The beginning of a cancer tumor that is just a few cells strong.
So how does TDA help find them?
There is an algorithm called MAPPER. It takes this high-dimensional cloud of single-cell data and simplifies it into a graph, a network of nodes and edges. It creates a simplified map of the data's shape.
And on this map, the rare cells stand out.
They appear as distinct flares or loops off the main structure. A standard statistical average would hide them, but the topological map preserves them as distinct features. It reveals the rare cell populations that might be driving a disease.
It's like having a map that doesn't just show the highway, but shows every little hidden path and dead end where the interesting stuff is hiding.
And it can even trace viral evolution. We can look at the shape of viral mutations over time.
Oh, wow. So we can see the trajectory of a virus.
We can map the landscape of possible mutations. By understanding the topology of that landscape, we can try to predict where the virus might evolve next, which paths are open to it, and which are topologically forbidden.
That feels incredibly relevant given the last few years. It's using math to outsmart evolution.
It is identifying the constraints of evolution. Evolution isn't random, it follows the path of least resistance. Topology helps us map those paths.
Okay, we have covered the digital world and the biological world. Now I want to go to the physical world, the world of matter. The outline mentions topological insulators.
This is where things get really strange. We are moving from the shape of data to the shape of matter itself.
And understand this, the notes say we need a quick history lesson on the Hall effect. I remember this vaguely from high school physics. It involves magnets, right?
Yes. Let's go back to 1879, the classic Hall effect. You have a strip of metal, you run a current through it, you put it in a magnetic field. The magnetic field bends the electrons to one side.
Like blowing wind on a stream of water. The water piles up on one bank.
Right. And that buildup of electrons on one side creates a voltage. That's the Hall voltage. Simple classical physics. Linear relationship. More magnetic field, more voltage.
Fast forward to 1980.
The quantum Hall effect. Scientists cooled the material down to near absolute zero and cranked up the magnetic field to intense levels. They found something bizarre. As they increased the magnetic field, the conductance, how easily electricity flows, didn't change smoothly. It jumped in steps.
Steps, like a staircase.
Discrete steps, perfectly flat plateaus. And the value of these steps depended only on fundamental constants, like the charge of the electron and Planck's constant, and an integer, 1, 2, 3.
It didn't depend on the material or how dirty the sample was. Usually impurities mess everything up.
No, that was the shock. You could have a dirty sample, a clean sample, a different shape. The conductance was exactly the same. It was quantized. It was eerily perfect.
And this is where topology enters physics.
Physicists realized that this integer, this 1, 2, 3, was actually a Chern number. It's a topological invariant. It's like counting the holes in the donut. The electron wave function in the material had tied itself into a knot.
So the electrical properties weren't about the atoms anymore. They were about the knot in the wave function.
Exactly. And because you can't have 1.5 holes in a donut, you can't have 1.5 conductance. It has to be an integer. It is robust. You can dirty the sample, you can deform it, but as long as you don't rip the knot, the conductance stays perfect.
But quantum Hall effect required massive magnetic fields. That's not practical for your laptop. The holy grail was to do this without the magnet.
Enter the quantum spin Hall effect and the topological insulator, or TI.
So what exactly is a topological insulator? It sounds like an oxymoron. Is it an insulator or a conductor?
It's both. A topological insulator is a material that is an insulator in the middle, the bulk, but a conductor on the surface.
So electricity can't flow through it, but it flows around it, like a chocolate truffle wrapped in foil.
Yes. But it's not just any conductor on the surface, it is a protected conductor.
Protected how?
Let's use the analogy of a moat. Imagine the bulk of the material. The inside is a kingdom surrounded by a high wall. No one can get in or out. That's the insulator part. But outside the wall, there is a moat. And in this moat, the water, the electrons must flow.
Okay, but normal wires conduct electricity too. Copper conducts. What makes the TI moat special?
In a normal wire, electrons can bounce off impurities. They hit an atom and bounce back. That creates resistance. Heat. That's why we lose energy in power lines.
That's why my laptop gets hot. The electrons are crashing into things.
Exactly. But in a topological insulator, the surface states have a property called spin momentum locking.
Spin momentum locking. That sounds technical. What does that mean?
It means the direction the electron moves is locked to its spin. Let's say spin-up electrons can only move clockwise around the moat, and spin-down electrons can only move counterclockwise.
Okay, so it's a one-way street for each spin type.
Precisely. Now imagine an electron moving clockwise hits an impurity. In a normal wire, it would bounce back. But to bounce back, to go counterclockwise, it would have to flip its spin.
Because counterclockwise is reserved for the other spin.
Correct. But here is the kicker. Time reversal symmetry. A fundamental law of physics in these materials forbids that spin flip without a magnetic field.
So the electron cannot turn around.
It physically cannot backscatter. It has no choice but to go around the obstacle and keep moving forward. It flows like water around a rock without losing momentum.
That sounds like superconductivity.
It leads to dissipationless transport, no resistance, no heat. The electrons flow perfectly along the surface because the topology of the system protects them.
That is mind-blowing. We're designing highways for electrons where U-turns are illegal by the laws of physics.
And that stability is exactly why these materials are the leading candidates for the next generation of quantum computers.
This brings us to the final, and perhaps most futuristic part of our discussion, the quantum computer.
We hear about quantum computers all the time. They promise to solve problems that would take conventional supercomputers millions of years.
But there's a crisis in the field.
Yeah.
We have to be honest about it. We've been hearing quantum is coming for 20 years. What's the holdup?
The crisis is decoherence. Current quantum computers use qubits, quantum bits. These qubits are incredibly fragile. A change in temperature, a tiny vibration, a stray electromagnetic wave, anything can cause the qubit to lose its quantum state.
It collapses. It forgets whether it's a 0 or a 1.
It decoheres. The calculation is ruined. It's like trying to build a house of cards in a hurricane.
Yeah.
You spend all your energy just trying to keep the card standing. We call that error correction, leaving very little energy to actually do the calculation.
So how does topology solve this?
By moving from local storage to global storage.
Okay, unpack that.
Imagine you want to send a secret message. If you write it on a tiny pebble and leave it on the beach, a wave might wash it away. That's a standard qubit. It's local, it's fragile.
Okay, it's exposed.
But what if, instead of writing on a pebble, you took a long rope and tied a knot in it?
A knot.
And you leave that rope on the beach. The waves can shake the rope. The wind can blow it. The rope might get twisted or buried in sand. But the knot remains.
The information, the fact that it is knotted, is stored in the whole rope, not just one part of it.
Exactly. You cannot untie the knot by just shaking it locally. To untie it, you have to cut the rope or pass the ends through each other. It is topologically protected.
So a topological quantum computer stores information in knots of the wave function.
That is the goal. And the star player in this scheme is the Majorana fermion.
The particle we teased at the beginning.
The Majorana fermion was predicted by Ettore Majorana in 1937. It is a particle that is its own antiparticle.
Which usually means they annihilate each other, right? Matter and antimatter go boom.
Usually, yes. But in the context of topological insulators coupled with superconductors, these Majoranas can exist as zero energy modes separated in space.
Where do we find them?
We find them at the ends of nanowires. Imagine a wire made of a topological insulator wrapped in a superconductor. At one end, you get a Majorana. At the other end, you get another Majorana.
They are paired.
They are paired, but they are far apart. Together, they form a single qubit. The information is delocalized between the two ends of the wire.
So if I disturb one end of the wire, I don't destroy the information because the information lives in the relationship between the two ends.
Exactly. It is inherently fault-tolerant.
And how do we compute with them if they're just sitting at the ends of wires?
We braid them.
Braiding.
Like hair.
Literally like braiding hair. But in space-time, if you have these nanowires and you move the Majorana fermions around each other, swapping their positions, you are braiding their world lines, their paths through time.
So the calculation isn't flipping a switch from 0 to 1. The calculation is the dance. The calculation is the braid. Because of the topological properties, and this gets into something called non-abelian statistics, swapping them changes the state of the system. And the beauty is, it doesn't matter exactly what path they take. It doesn't matter if your hand shakes a little while you move them.
All that matters is, did particle A go around particle B?
Yes or no, it's digital, it's topological. It eliminates the noise problem because small wiggles don't change the braid.
That is incredibly elegant. It turns computation into a dance of geometry. It feels so much more robust than trying to balance an electron in a trap.
It is the ultimate realization of the idea that shape is memory.
So, are we close to building this, or is this still science fiction?
We are getting closer. The research shows significant progress. Scientists have captured high-resolution images of these topological quantum Hall-edge states. We are moving from pure theory to actually engineering topological qubit arrays.
So it's no longer just a blackboard equation, it's becoming hardware.
It is becoming engineering. Microsoft and other major players are betting heavily on this topological approach because if it works, it solves the error correction problem that is plaguing everyone else.
It's the high-risk, high-reward path.
But the reward is a computer that can model molecules, crack codes, and optimize systems with a power we can barely comprehend.
This has been a wild ride. We started with donuts and coffee mugs, moved through pruning AI brains, mapping viral evolution, built a moat for electrons, and ended up braiding particles to build a supercomputer.
And the common thread through all of it is topology.
It really is. It's this realization that looking at individual points, whether they are data points, atoms, or qubits, is not enough.
That is the synthesis. We are witnessing a shift in the scientific paradigm. For a long time, we were reductionist. We thought if we understood the smallest particle, we understood everything.
But topology said, no, look at the whole.
Look at the connectivity. Look at the loops. Look at the knots. The interesting properties intelligence in AI, robustness in biology, superconductivity in physics emerge from the global structure, not the local components.
It's the global geometric imperative. The shape of the system holds the key to its potential.
Whether you are a biologist, a physicist, or a data scientist, you are ultimately becoming a geometer. You are studying the shape of complexity.
And I think that is a profound place to leave it. We often get overwhelmed by the amount of data in the world, the noise. But maybe if you just learn to look at the shape of it, it's not as chaotic as we think.
It might just be a beautiful, complex knot waiting to be untied.
Before we wrap up, a heartfelt thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support. And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content and support us in Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.